We're all getting used to seeing movies in 3D, and soon we'll even have 3D television sets in our living rooms. But have you ever stopped to wonder if there are more than 3 dimensions? How would we know? That's what world-famous theoretical physicist Lisa Randall gets paid to think about every day. Shining City caught up with her at Harvard to talk about string theory, extra dimensions, and why she isn't afraid of experimenting with the Large Hadron Collider that some doomsday predictors warned could create a black hole big enough to swallow the Earth.
We just don't know why there should be only 3 dimensions, so it's worth thinking about, could there be other dimensions of space that we simply don't see? I mean, we, after all, have limitations to what we can see. We see through our senses. It could be that there are dimensions that are hidden in some way. They could be really tiny so we don't see them. What we realized is they could also be very curled or curved in a way that could hide them.
How does time fit into all of this?
Well, so what Einstein taught us is that we should think of space and time together. But one thing that confuses people is they think, well, time's just another dimension. We don't know how to make sense of a theory with more than one dimension of time. So there's really always going to be the single time, at least in our current version of how we think about things, although there could be more dimensions of space.
Okay, so you're out there looking for some new ways of looking at space or new dimensions of space. How do you find them? How would you detect them?
That's a good question. I mean, we haven't seen the dimensions, so that puts a lot of constraints on what their properties could be. What we could see are particles that actually travel in the other dimension, even if we're not directly traveling in these other dimensions and we only directly experience 3 dimensions of space.
So there are experiments going on right now in Europe with the Large Hadron Collider. What does it do, and how might it help you actually find out a little bit more about these other dimensions?
So the Large Hadron Collider, what it does is it accelerates protons to enormously high energies and then collides those protons together. And because of Einstein's famous equation... What does it
look like? What is this collider? How is it built?
First of all, it's in Europe. It's near Geneva. And it's a 27-kilometer ring underground. But the tunnel is big enough that you can walk through it when it's open. You don't want to do that when there are protons going around, but you can walk through the tunnel. And it has beams of protons. And those beams of protons collide together. So what happens is there are electric fields that accelerate them to high energies. Then there are magnets that bend them around so that they stay in the ring. So they go around the ring 11,000 times a second, and each time they get kicked and accelerated. So they can be accelerated to enormously high energies. Then, when they have this high energy, because of the magic of E equals mc squared, they can turn into heavy particles.
Are there sounds inside the collider?
I don't know the answer to that. I mean, it certainly can be, but it's usually machinery you're hearing.
So are we turning them into particles from another dimension?
We could be.
What about black holes? People were concerned. I remember when you were starting to collide these protons that you might create small black holes.
Well, you know, you could be concerned about a lot of other things that are a lot more likely to happen. But also, in this case, we've actually, even though we haven't had these collisions on Earth, there have been these high energy collisions out in space from cosmic rays. So if this had really been happening, if it really had been a danger, we wouldn't see the Earth, or we wouldn't see the sun, or we wouldn't see neutron stars. You can see that there are objects that had stuck around, that if there really were these black holes that could be created, we would never have seen. So we're very confident that this is not a danger.
I've heard that you were initially attracted to a career in science because of the certainty that math and science offered, but you've gone into a field that seems to have nothing but uncertainty. So how do you reconcile that?
It's really interesting, and I think it's one of the great things about science is the combination of certainty and having answers and having definite methods, and the uncertainty of having these great, big, enormous questions that you don't yet know the answers to. And it's true, when I first started off, I liked the certainty of mathematics. I was growing up at a time with a lot of upheaval, and I liked the certainty. But of course, that wouldn't be interesting if you're just answering questions that everyone knows the answer to. That gets boring after a while. What's really fun is being able to apply what you know in your methods, but to be able to branch out and develop new ideas and new methods to answer questions that we haven't answered before. That's what makes science interesting.
Okay, so my last question is going to be probably a little bit unfair because your very job title has the word theoretical in it. But looking 100 years into the future, how would you imagine that some of the questions that you're trying to answer today, how might they change the world?
Well, I think the one thing we've learned is no one ever gets that good answer that question correct. I mean, there are such dramatic changes and we don't anticipate them, and that's one of the beauties of science, that we know, I mean, what's amazing is we know how to make progress. We have definite questions in mind, but it could be some small, apparently insignificant inconsistency that then could lead to a whole new field, a whole new idea. So since you were unfair, I'll be unfair and actually skirt the question, but I'll say that what we do know is it's going to be nothing like anything that we're going to anticipate now.